The fire triangle gives us a basic understanding of the components needed for fire to exist. Fuel, such as grass, timber, mulch, or anything else flammable, is the first component of the triangle. In order for fuel to combust, oxygen is needed. Finally, some type of heat source must initiate the combustion. For wildland fires, this often takes the form of a lightning strike, a spark from a downed power line, or an ember from a fire pit landing on easily combustible material. A vast majority, nearly 85%, of wildfires have a human ignition source, whether it be intentional or not. Once these three criteria are met, fire can occur. In the absence of any one factor, fire will not burn. Fire ecology is a branch of ecology focused on understanding the complex web of interactions influencing wildland fire and its effects on abiotic and biotic ecosystem components. Abiotic factors, such as weather and topography, affect how a fire burns and spreads, while fire can also affect localized weather by creating currents of hot air that can generate significant winds. Biotic factors, such as flora present at a site, also influence how a fire spreads by providing fuel for the fire to consume. Fire is natural and healthy on many landscapes, and plays a significant role in vegetation control, habitat creation, and other ecosystem services. The graphic seen here highlights the connectivity of these three factors. Wildland fire specifically is any fire in natural environments, from grasslands to dense forests. The process of planning, preventing, and fighting fires is called fire management, and goals of fire management can range from the protection of human life and property to advancing forestry, wildlife, and land use objectives. Climatic changes, namely warmer temperatures and less summertime precipitation, have been seen across the country and have led to an increase in the presence of wildfire, creating longer fire seasons, which complicates and increases the costs of fire management. The post-ignition fire behavior triangle shows a simplified example of the factors that contribute to the severity, intensity, and movement of a fire. Fuels affect post-ignition behavior by influencing how a fire can burn and move, including the flame length, or how big the flames are, as well as the ability of a fire to jump from the surface to the canopy. The size, type, arrangement, and moisture content of fuels play significant roles in determining fire behavior, which is also altered significantly by weather and topography. Weather influences the direction in which fire travels, as well as the rate at which it spreads. Warmer, drier, and windier conditions allow fire to proliferate. Wind aids in fire's horizontal movement, while warm, dry conditions create favorable fuel conditions for fire to ignite. Residence time refers to the duration in which a fire stays in one particular area. A fire that ignites on a warm, dry, windless day may have a longer residence time. Increasing the residence time of a fire can increase the severity, causing more significant impacts on soil health due to longer heating times. Additionally, trends in severe weather, such as frequency of lightning strikes, can affect the number of ignitions in a given area. Topography also influences fire behavior. Fire generally burns uphill. Think of holding a lit matchstick and watching the flame move up. That means steeper areas encourage the spread of fire. Additionally, smoke and warm air from a fire downhill will preheat and dry uphill fuels, creating more flammable conditions. Conversely, a fire at the top of a steep slope can pose challenges by increasing the risk of burning logs rolling downhill, which can spread fire and endanger the lives of firefighters below. Aspect, or what cardinal direction a slope faces, also affects fire behavior. Aspect of a slope influences weather, with south-facing slopes in North America receiving the most direct sunlight, causing more drying of fuels. Slope also affects wind and can create microclimates. Understanding local trends and patterns is important when thinking about fire management plans. Finally, barriers influence fire behavior. For example, rivers can act as a fire break, discouraging fire from moving beyond them. Fire intensity is the amount of energy produced by a fire and is determined by the temperature at which the fire burns and its residence time. Fire intensity is often summarized by the fire type, as demonstrated in this graphic. Ground fires burn surface fuels, such as peat, duff, and litter, and are generally low to moderate severity. Surface fires stay on the forest floor and burn lower vegetation, such as grasses and small shrubs, and is characterized by low to moderate intensity. Subcanopy fires burn understory trees and low shrubs, and are of moderate intensity. Crown fires release significant amounts of energy and are therefore classified as high intensity and occur when the tops of big trees ignite. While fire intensity is a measure of the energy output from a fire, fire severity is more descriptive of the outcome of a fire and the impacts it had on the local ecosystem. A stand-replacing fire that causes near-total mortality in the dominant vegetation would be a high-severity fire. But if the ecosystem that was totally burned was a grassland, it may be a low-intensity fire, whereas if the ecosystem was dominated by Douglas fir, the stand-replacing fire would be high-intensity. This is because the amount of energy released in the burning of Doug fir is much higher than that of burning grasses. Stand-replacing burns cause significant releases of carbon from all pools, as they are lethal to the dominant vegetation and substantially change the vegetation structure. They can take the form of crown fires, but can also be highly severe ground fires, which have long residence times. Similarly, an understory fire may be high severity in terms of shrubs and grasses, but relatively low intensity. These burns generally release carbon stored in surface pools, but larger carbon stocks below ground and in live, mature trees are generally left intact. Mixed severity fires are common, as shifts in fuels, weather, and topography can create a wide array of burn types in one fire complex. This can also be a result of heterogeneity in stand age and species composition. Fire severity varies widely based on many factors, including the vegetation present. Many landscapes need fires of differing severities and intensities to maintain their natural characteristics. These graphics demonstrate different severities and intensities of fire. The graphic on the left shows a stand-replacing fire. This depicts a forest where fires are rare, whether due to natural reasons or human-influenced fire suppression. In this graphic, a significant amount of surface fuels have accumulated, including grasses, logs, woody debris, and brush. Additional ladder fuels, like shrubs, small understory trees, and snags, are also present. Given the proper conditions, surface fires will spread quickly, moving up ladder fuels towards the forest canopy. From there, the canopy can ignite, creating intense fires that result in high mortality, and therefore are high severity. Carbon pools are where carbon is stored in an ecosystem. For forested ecosystems, there are 5 main pools that we think about: soil organic carbon, live below ground, namely roots, live above ground, mainly in trees, litter, and deadwood. The graph here highlights some of the main forest types in the southeastern United States and where carbon is stored in each. For most forest types in the region, soil organic and live above ground are the largest pools. The amount of carbon stored in each pool is influenced by physical traits and growing patterns of flora, but is also significantly influenced by the presence of fire on a landscape. For example, ground fires are most likely to reduce the amount of soil organic carbon and litter, and to burn some deadwood as well. In general, these fires will not have significant impacts on live above ground carbon, assuming the fire is burning in a relatively fire-adapted ecosystem. Meanwhile, ground fires will generally be high severity, removing carbon from all the previously described pools. Keeping carbon pools in mind when using fire on a landscape is important, and understanding where carbon is stored in different forest types can help land managers further carbon-related goals more effectively. Disturbance ecology is another important piece of the wildland fire puzzle. It is a study of how events alter the structure of an ecosystem, community, or population and change resource availability. Fire affects trees in many ways, and its effects depend on 3 major factors. First is fire resistance, which is how resistant any given tree is to different degrees of fire. For example, a tree with thick bark, like the ponderosa pine, is generally more fire resistant than a thin bark tree, such as the quaking aspen. Secondly, recovery from fire damage affects the interaction between fire and trees. If a tree does experience damage as a result of fire, its ability to survive will affect the overall mortality rate of said fire. Finally, tree recruitment plays into disturbance ecology. Some trees, such as the jack pine, have serotinous cones, which means that high heat is required in order for the cones to open and regenerate. Separately, the quaking aspen will spread shoots out after a disturbance, allowing for rapid regeneration given the proper site conditions.